Hello students, welcome back. Previously you have heard me mention the conservation of energy, and I stated that the law of conservation of energy says that energy cannot be created or destroyed, it can only be transformed between different types of energy. The way we can write that concept into an equation looks like this. Okay, here I've written the initial mechanical energy is equal to the final mechanical energy in a given process. Okay, basically what this is saying is that the total energy before a process occurs is equal to the final energy after a process occurs. Last video we defined mechanical energy as the combination of potential and kinetic energy. It's just the sum of both those energies. So if I write that out more explicitly, this equation turns into this. Okay, so writing out mechanical energy as potential energy plus kinetic energy for both the initial and the final, I get the initial potential plus initial kinetic is equal to the final potential plus the final kinetic. This equation pretty much captures the conservation of energy for a system with energy that is transforming between potential and kinetic energy. Okay, next I'm going to go through a common example that you might see where you can use this equation. Okay, here we have a ball sitting on the edge of a cliff that has a height of 12 meters, and we can say this ball has a mass of 5 kilograms. Okay, let's say we wanted to test this equation to make sure that the energy before it falls is equal to the energy after it falls. So first we're going to find the energy before it falls, the initial state of the ball. Okay, so first I'm going to calculate the potential energy and then the kinetic energy. I'm going to assume that at the top of the hill it hasn't moved yet. It hasn't started rolling off the hill yet. It's just sitting there, but it's about to fall off. Okay, so in that situation, the potential energy is going to be equal to mgh. Okay, we mentioned already that g is equal to 9.8. So if I plug in these numbers, I'll get this. Okay, so here I have 5 for the mass, 9.8 for g, and 12 for the height of the cliff. And if I plug this in my calculator, okay, I get that the potential energy initial is 588 joules. Okay, so I'm going to keep that to the side. Okay, now that I know the initial potential energy, I'm going to go ahead and try to figure out the initial kinetic energy. Okay, I know that kinetic energy is equal to 1/2 the mass times the velocity squared. And I know that initially, the initial kinetic energy is going to have the initial velocity. So I put a little I to notate initial there for velocity. And as I said before, we're assuming that at the top of the hill here, the ball is not moving yet, so it has a velocity initial of 0. Okay, because it has no motion yet, anything times 0 is 0, so the kinetic energy is going to be 0. Okay, so I know my kinetic energy initial is 0 joules, my initial potential energy is 588 joules, so if I do that in this equation, I know that my initial total energy is going to be 588. Okay, now I'm going to figure out the final state and see if that is consistent and see that the final state added up is also 588 to show that the conservation of energy is applied to this example. Okay, so to figure out the final state, we need to first figure out, okay, what's happening in the final state of this process. Okay, well, we know that initially it's on the top of the hill. After it rolls off the hill, the final state is going to be right whenever it's landing. Whenever it's landing, the height of the ball is going to be 0 relative to the system. Okay, if I know that the height is going to be 0, I know I can figure out the potential energy pretty easily, and let's do that right now. Okay, I know potential energy is mass times g times the height. If I plug that in for the final state, I get this. Okay, I know that since the height is 0, anything times 0 is 0, so the potential energy final is going to be 0, just like the kinetic was 0 for the initial. Okay, so that means that the total final energy is just all going to be in the kinetic, which makes sense, right? Because the potential is turning into kinetic as it falls down, and whenever there's no height, it's going to be all kinetic. So let's go ahead and figure out what the kinetic is going to be there. Okay, I know the final kinetic energy is going to be equal to 1/2 the mass times the final velocity squared. I don't know the final velocity yet, so I'm going to have to figure that out. And the examples that you're going to be working with, you're probably not going to have to do something as challenging as this, but I'll go ahead and go through this, and we'll actually use an equation that we used in the past. This is a free-fall problem, right? Where you have something falling from gravity. So we did these problems back in the last couple units with projectile motion. So I'll use some of those equations to figure out what is the velocity right before it hits the ground. Okay, I dug into my old kinematics equations for projectile motion, and I found these two that are going to help me find the final velocity of the ball as it's reaching the ground. I'm trying to find VF. I know VI and the initial velocity is 0. So to find the final velocity, I need to find time. I know acceleration from gravity is 9.8, so I have that, but I need to find time. Okay, the way I can find time is by using this equation, because I know the vertical displacement dy is just the height, so I know this is going to be 12. I know g is 9.8, and I can solve for time here, knowing those two variables. Okay, if I isolate time in this equation, this turns into this equation. Okay, so I get time is equal to the square root of 2 times the vertical displacement, or the height in other words, divided by g, which is 9.8. And just a really quick rundown how I got that from this equation. I had to multiply 2 to both sides, so they canceled this 1/2 and multiplied the 2 to the dy. That's why you have that here. And then I divided g to both sides because it's being multiplied, which is why it's being divided here. And then to get rid of the square, I took the square root of both sides. So then it left me with t by itself is equal to this stuff. Okay, if I plug my numbers in here, I end up getting the square root of 2 times 12 divided by 9.8 in my calculator. I get this. Okay, I got 1.56 seconds. Before I plug in time into this equation to find the final velocity, I'm going to multiply t to both sides so that I have my final velocity isolated so that I can solve for it. Okay, so now I know time times the acceleration is going to be equal to the final velocity. If I plug my numbers in, I get this. Okay, I have 1.56 seconds times 9.8 meters per second squared, which is going to be equal to 15.28 or 29. Okay, I know we're getting a little cramped here, but I finally got my final velocity. It's 15.29 meters per second. So I'm going to erase all this stuff and plug it in right here and figure out the kinetic energy. Okay, so now I know that the kinetic energy should be equal to 1/2 times 5 kilograms, the mass, times 15.29 meters per second squared. Alright, if I plug this in my calculator, I should get something close to this. I did round some numbers, so it might not be exact, but let's just double check. Okay, I ended up getting 584.5 joules. And the only reason I got something that was slightly off of that is because I rounded some numbers so that I didn't write a bunch of decimal points on the whiteboard, and I was already getting really cramped. So it's close enough. We can see that the initial energy is equal to the final energy, which again proves the conservation of energy applies, and it's easy to see in a system like this. So I hope that this example makes this concept make more sense as we go through and finish this unit for conservation of energy. Thank you guys, see you next time.